Welcome everyone. We're moving right along into lesson 3, exponential models. Today you will be able to write exponential models in different ways to solve problems. So you guys are going to have 2 different formulas today. It's all going to be formula work. So if you can plug formulas into a calculator, you are good to go here. So the first formula we're going to look at is compound interest. So compound interest is interest that is paid on both the principal amount and on the interest that has already been paid. The compound interest formula is an exponential growth function. So again, compound interest is primarily seen in banks, savings account, that type of thing. It's very much the financial side of mathematics. So let's take a look at our compound interest formula. So it's A is equal to big P, parentheses, 1 plus R over N, close parentheses, to the power of N times T. Lots of variables to be accounted for here, and you want to make sure you're plugging them into the correct spot. So let's go over what each of the variables represent. So, capital A, that is the amount paid, also known as the ending amount. So it's just, all right, after putting so much money in for how long, what's the end amount? All right, the P, that is called the principal amount, also known as your starting amount. So, how much money did you put into the account at the start? $20? $5,000? How much did you put in? You guys already know R. R is the rate as a decimal. Always have to convert that percentage to a decimal. All right. N is the number of times compounded, because depending on the account, it can compound once a year. It could compound 300 plus days a year. So it all depends on what the account calls for. And then T, you guys are already familiar with T as well. T is time in years. And all right, so let's now talk about the most common values that N could possibly be. There are 4 common types that N can be. You can have it be compounded annually, quarterly, monthly, or daily. So depending on what the problem tells you, that is what your N is going to be. Compounded annually, your N is equal to 1. Compounded quarterly, N is equal to 4. Monthly, N is equal to 12. And then daily, N is equal to 365. So you need to make sure you read the problem correctly. All right? So now let's get into some problems. So Matthew invested $680 in an account paying an interest rate of 5.8% compounded daily. Assuming no deposits or withdrawals are made, how much money to the nearest $10 would be in the account after 11 years? So let's identify all our key pieces. P, R, N, and T. So our starting amount is 680. Our rate is 5.8%, but we have to write it as a decimal. So 0.058. N, it says it's compounded daily. So daily, 365. So N is 365. And then T, 11 years. So now we need to find the total amount. So now we have all our variables. So we just need to plug in. A is equal to 680 times 1 plus 0.058 divided by N, so 365 to the power of 365 times 11. Now, if you are absolutely careful with your calculator and you take proper measures with parentheses and whatnot, you can plug this whole thing into your calculator. Personally, I am going to break it up. I'm going to simplify everything inside the parentheses and our exponent, and then I will plug it into the calculator. So 680 plus 1. So we get 1.00015. Actually, that would be a 6. If you do this, keep as many decimals inside the parentheses as you can. Then 365 times 11, 4,015. Now I'm going to plug this whole thing in. And we get $1,286.96, but it says to round to the nearest $10. So this is going to be $1,290. So make sure you follow what they want you to round to. All right, let's do another one. So Sarah invested $8,000 in an account paying an interest rate of 3.5% compounded quarterly. Assuming no deposits, no withdrawals, to the nearest cent would be in the account after 8 years. So our starting amount is $800. Our rate is 3.5%, which would be 0.035. Our N, this is compounded quarterly, so it is 4. And the amount of years is 8. So A is equal to 800. 1 plus 0.035 divided by 4 to the power of 4 times 8. And again, I'm going to simplify inside the parentheses and my exponent before calculating the total. So we get 1.00875 inside the parentheses. So 800 times 1.00875 to the power of 32. All right, and then this one's to the nearest cent. So that's what we like to see. So $1,057.22. So there we go. All right. Now, they may ask you at times to work backwards to find something. So this last example that we have is working backwards. Luke is going to invest in an account paying an interest rate of 5.9% compounded monthly. How much would Luke need to invest to the nearest cent for the value of the account to reach $1,500 in 7 years? So we need to find P. We need to find the starting amount. So our ending amount is $1,500. Our rate is 5.9%, which is 0.059. Our N, this is compounded monthly, so it's 12. And our T is 7 for 7 years. So we're finding P. We start with A. So how our equation is going to be set up is 1,500 is equal to P times 1 plus 0.059 divided by 12 to the power of 12 times 7. Yeah, so now we're going to have 1,500 is equal to P. I'm going to simplify inside the parentheses. So we have 1.00492 to the power of 84. Now, what I would highly recommend, since we have to solve for P, just divide both sides by our exponent. It'll make your life a whole lot easier. So 1,500 divided by 1.00492 to the power of 84. And there we go, our starting amount, $993.50. This makes sense because our starting amount is always going to be lower than what we ended up with. So if you get a bigger number here for your starting amount, something went wrong. Your starting amount should always be smaller than the ending amount. All right, we have one more example of compound interest, and then we have one more formula to talk about.